All right, so what's the possibility of life? So we've talked about that there really are extrasolar planets, so what about the possibility of life out there? So based off of very simple assumptions, we definitely get the idea that there could be life out there. So to try and help us figure out how much life, or more particularly, if there are intelligent communicating civilizations, Frank Drake developed what is now referred to as the Drake equation to help us kind of figure out how many are out there. Now, something that I kind of want to stress is, although this may make a prediction of how many intelligent species are out there, the better way of viewing this is kind of as a guide of what are the things that we need to know to figure out if there are any communicating civilizations out there. So the Drake equation is capital N equals R sub star, F sub P, N sub E, F sub L, F sub I, F sub C, and capital L. Now, this looks really, really bad, but it's hopefully not too bad once you understand all of the pieces. So the idea is that we're looking for capital N, the number of communicating civilizations in our galaxy right now. Then, to figure out that number, we start from the broadest things necessary for life, and then we slowly cut it down smaller and smaller until we come to some sort of number that gives us an idea of how many civilizations are out there. So starting with R star is the formation rate of stars within our galaxy. We don't expect that life is going to develop without a star, so we're going to start with stars. Then, we don't expect life to start on a star itself, so we're going to have planets. That's F sub P. What fraction of stars actually have planets? Then, we now have a star and planets. How many of those planets are Earth-like? Now, what we mean by Earth-like is have liquid water. That's it. That's all we mean by Earth-like, is that it has liquid water on the surface. Now that we have planets with liquid water, what is the fraction of those planets that actually produce life? That's F sub L, fraction of life-bearing planets. Now, just having life doesn't mean we're going to be able to talk to it. So we need intelligence. So what is the fraction of life-bearing planets that actually produce intelligent life? This is F sub I, fraction of intelligent life. Now, just having intelligence doesn't mean we're going to be able to communicate with them. They're going to have to produce technology and communication. This is F sub C, the fraction of intelligent species that develop communication. Then the last factor is how long is one of these things going to last. If they are produced and then immediately die within a relatively short amount of time, we're not going to have a chance to actually see them. So the longer the civilization lasts, the greater the chances we'll actually see them. So this is capital L, how long one of these civilizations actually last. So let's go through each of these pieces. Now, we actually have some good values for some of these things. For example, the star formation rate and the fraction of planets, of stars that have planets. However, there are other things that we just don't really know. So starting with the star formation rate, we can actually put limits on the types of stars that we could expect to produce communicating civilizations. For example, our own civilization has taken 4.5 billion years before we actually developed. Okay, so this means that any star that dies before 4.5 billion years is probably not going to give any life long enough to develop communication. So any stars greater than 1.5 solar mass are out. They die out too quickly. On the other side, smaller stars, which are cooler, will mean that the planets have to be closer in. And if a planet is too close in, then it is more likely to have synchronous rotation. Synchronous rotation is where the rotation and the orbit take the same amount of time, so that only one side of the planet is facing towards that star. Well, the side that's facing towards the star is always going to have daylight and therefore get super, super hot, and the side that's always facing away is going to get super, super cold, neither of which are good for life. Another problem with these super small stars, the red dwarfs or M dwarf stars, is we've actually seen that they have frequent and violent solar storms, the solar flares, which, for a planet that's really close in, is going to be really, really bad for life. So it appears that this sort of planet, or these sorts of stars, the ones that are in the right range that are going to last long enough and have planets at a good distance, probably form about once every year. So our star is about 1. Now that we've got stars, what fraction of stars have planets, F sub p? Well, as we've been studying and looking from various sources, this appears to be anywhere from about 70% to 100%. In other words, planets are actually very, very common. Now, the number of planets in the star system that are Earth-like is a lot harder to determine. So again, what we mean by Earth-like is have liquid water. A lot of this is going to depend on the habitable zone. The habitable zone is the distance away from a star where the planet gets enough sunlight that it's not cold, but it doesn't get too much sunlight so it's not super hot and baked. Okay, so, for example, in our own solar system, the Earth is very nicely positioned in the habitable zone. Venus is too close and Mars is too far away. Mars actually makes me kind of sad. We have very strong evidence, geologic evidence from Mars that it actually did once have liquid water, about 4 billion years ago. But because Mars is small, so it's smaller than Venus and Earth, it actually lost a lot of its internal heat and therefore geology stopped. Because of this, it lost its magnetic field, which protected it from the solar wind, and it appears that volcanism may have ended, which means it no longer has outgassing to help produce an ongoing atmosphere. So, as it has lost more and more atmosphere, it has decreased the greenhouse effect and has essentially just frozen. So, Mars may have actually been could have had life at one point in the past, but it doesn't seem to be able to anymore, which is just sad. So if Mars was Earth-sized or maybe super Earth-sized, maybe it could have still been habitable today. Anyway, looking at the size of the habitable zone, with a small star, the habitable zone has to be really close in. Then, as we get to hotter and hotter, larger and larger stars, the habitable zone gets pushed out farther and farther away, and it also gets wider. So for an M dwarf star, it's super close in. For our own solar system, it's farther out to where the Earth is. And in a larger star, maybe we could even get Jovian planets that are within the habitable zone. Now, we don't expect the Jovian planet itself to harbor life, but maybe its moon could. Maybe the moon could be Earth-like. Now, another possibility for Jovian moons is something like Europa. Europa is one of the moons around Jupiter, and as we've studied it, we have very clear evidence that it has a subsurface liquid water ocean. The top layer we see is actually frozen ice. Yes, I realize that was redundant. Is ice, but below that, we think that there's a subsurface liquid water ocean that is kept warm because of the gravitational interaction between Jupiter and Europa. So, even though Jupiter's not in the habitable zone, Europa might be considered habitable. So, with all of these things, we have less information on this, but we're hopefully getting there. We'll talk about it more in just a second. But N sub E appears to be anywhere from 1 out of every 10 solar systems has one Earth-like planet, or it might be as high as 2. We know that the Earth is habitable, Mars is close, and Europa seems like it could be. Now, a lot of our data that's helping us try to figure this out actually comes from Kepler, which we mentioned previously. So it found over 4,000 planet candidates, with 160 of those being in the habitable zone of its star. The new mission, the follow-up to Kepler, is the TESS mission, and it has actually already found a couple of habitable planets. Now, as we get through the back catalog of Kepler data, and we analyze the new data coming in from TESS, we're going to get a much better feel for N sub E. Kind of the current thinking is that it's about 20%, that about 1 in 5 star systems actually have a habitable planet. So we now have a planet with liquid water. Again, that's all we mean by habitable or Earth-like is just liquid water. So what fraction of planets with liquid water actually produce life? This is completely unknown. That's not true. We know that the Earth produced life. That is one data point, and what that tells us is that it is possible. But that's about it. So the fraction of habitable worlds with liquid water that actually produce life could be anywhere from 1 out of every 100 to maybe it's guaranteed that life, if it can get a hold, will. The next step is the fraction of life-bearing planets that produce intelligent life. Again, this is something that we know that has happened on the Earth, but that, again, only tells us that it happened. And even then, if you watch the news, you really question how much intelligence is actually on the Earth. Well, the fraction of intelligence of life-bearing planets that produce intelligent could be 1 out of every 1,000, or maybe it's guaranteed. Something about natural selection and evolution pushes towards intelligence. So how many of these intelligent species actually develop communication and technology? Again, we know we can do it, but that doesn't tell us a lot. So it could be 1 out of every 1,000 of these species actually develop communication, or again, maybe there's something about intelligence that strives for technology and communication, so that it's 100%. The last piece is the lifespan of one of these civilizations, and again, this is completely unknown. We know that we've had technology where we could be detected by stuff out there for the last 90 years or so, starting in about the 1930s. However, how much longer we're going to last is, again, completely unknown. It could be that in the next few years, World War III erupts and it goes full nuclear and we wipe off all life off of the face of the Earth. Possible. Maybe, somehow, all of humans' different cultures overcome their differences and actually create a global civilization that's going to last for thousands of years. Also possible, maybe not likely, but possible, and in that case, we'd last a lot longer. Unfortunately, we don't know what the future holds for ourselves, and we absolutely don't know what's going to happen to other civilizations. So the lifespan, how long one of these civilizations lasts, could be anywhere from 100 years to maybe 1,000 years. All right, so what does this mean about the possibility of life in our own galaxy? If we take the most optimistic view, by optimistic, we're going to take the largest number at every single step. This suggests that there should be millions of communicating civilizations right now in our own Milky Way. This is Star Trek. If you've ever watched Star Trek TV shows, there's always new life and new civilizations every single episode. So no matter where you turn, there's new stuff out there. That's the optimistic view. If we take the most pessimistic view, which is where we take the smallest number at every step, then this suggests that there's only 1 for every 10 galaxies. So what this would mean is not only are we the only intelligent communicating civilization in the Milky Way, we are actually the only intelligent communicating civilization in the entire local group of galaxies. In other words, it is just us. There is no one else. Personally, I really don't like that one. It makes me feel alone and sad. I also don't like this view of millions of civilizations simply because the evidence is not there. We see absolutely no evidence or that there are that many civilizations out there. So I still kind of like to be optimistic. I kind of like the idea that there are a few, maybe even 1,000 scattered throughout the entire galaxy. But this is complete opinion. I have no scientific evidence for any of it. So we get the idea that there at least could be intelligent communicating civilizations out there. So we have started the search for extraterrestrial intelligence. This is SETI, and it has been going on for over 50 years. SETI is a group of individuals and universities, and their goal is to try to find some signal from an intelligent species. What they do is they get time on radio telescopes, and then they just record radio coming from likely targets, from places that might have intelligent life. Now, the hardest thing that they have is analyzing. It's a few individuals and a few universities. It's not a really large global network by any means. However, they get lots and lots of data. So the hardest thing they have is actually getting through all of that data. So to help with this, they've actually started a citizen scientist initiative called SETI at Home. If you're interested, go ahead and Google SETI at Home. What it is a program that you can download and install on your own personal computer. And when your computer would actually go into sleep mode or screensaver, it will download a packet of data and start analyzing it. Personally, I think it would be really, really cool to be able to say it was my computer that found the signal, but